Okay, so I apologize. I had a meeting that was set for 11:30. I was scheduled to give this recitation, so I'll finish a few moments earlier so I can get back to my meeting. And I'll do actually a recitation which is different than you're used to. I didn't prepare some sheet with all kinds of questions. I'll construct a question, show what I'm thinking about it, why I construct it this way, and I think it's useful to you also to understand how you're thinking about things and how exams are constructed. Okay, so what do I want to do? I want to do something that is connected with all that we did in the last few lectures. We want to try to understand how to implement all the stuff that we learned in linear algebra, the postulates of quantum mechanics, and so on. Okay, let's start from some kind of experiment. So let's assume in some hypothetical world that I have an experiment that measures consistently only 3 values. For to be explicit, -1, 0, and 1. Okay, first question. What can I conclude from this result regarding how should I construct my quantum mechanical description of this system?
This is the distribution. I mean, this is
no, I had a very simple statement. I'm repeating this experiment many times, and for all times that I do this experiment, I see only 3 precise results: -1, 0, 1. Nothing else. So my first question is, what can I say about the quantum mechanical description of this experiment?
The greatest probability is to get these values? What do you mean?
No, it's not probability. I said you won't get any other result except for -1, 0, and 1.
Maybe it's the eigenvalues.
Okay, right. It's an eigenvalue of something. Clearly, that's what the postulates of quantum mechanics tell you. What is this something?
Depends on what you measure.
No, I'm asking mathematically. What is this something? What have we said repeatedly? That in quantum mechanics, observations are eigenvalues of an operator. Okay, so these 3 are eigenvalues of something. Now, what can I say about this situation? Give me permission, if that's any operator. I have here a very important piece of information. We have 3 values.
Also, the eigenvalue.
So the size of my Hilbert space has to be 3. That's the first thing I can figure out from this information. And if it's 3, it's a finite. Therefore, I It's the most general way functions and write that. When I'm writing it in this way. Probability of measuring some eigenvalue is the eigenvector amplitude squared. So what do I know? This is 0. This is half. This is half. So,
therefore,
I have a question.
sure.
I don't get it why we separate the probability to measure -1 to only A.
Because the only part of the wave function, of the wave vector in this case, that will give you a result, a projection on the eigenvector of that gives you -1 is only this part, right?
Okay.
What is special about eigenvectors of an operator? They're orthogonal, and if I want to measure the system with a given eigenvalue, it corresponds to the eigenvector that has this eigenvalue. So this is all I have in the game. First, normalization. After step is 1, Okay, but that's A squared and B squared. So, very good question. Okay, in principle, you are right. I could have written right? They will fulfill the So I work more generally. You have an infinite number of results that fulfill this. So, in principle, results, I'm unable to say what is alpha and beta. Any alpha and beta, what is therefore, when I use this measurement, I don't get, in general, the exact structure. What can I do? First of all, I can write it in this way. Right? Okay. Now, very general multiply it by this. By e to the power I some alpha. It's a gauge invariance. You can always stick this and it won't make any difference in anything you will calculate.
So I can use the simplest one, right?
So you use the simplest one.
Okay, good.
Just put your one. Why complicate life?
Okay, good.
This phase, to shorten it, I'll just call it gamma. Can have an influence, and we'll see it in the next stage of this question.
For now, we use just the above.
No, what I'm going to tell you, how do you, now it's information that you probably have learned in the course in waves, how I differentiate between two incoming waves. What kind of experiment can I do in order to differentiate two incoming waves? I have a wave, and let's say if you square it, you'll see some. But if I take two waves and I want to see that are identical but have a difference in phase, how do I know what is the difference in phase? Interference.
Yeah.
What we have to do for interference, look at either different positions in space, right? See if at some point it adds, at some point it subtracts from each other, or you can wait and do a time experiment. See how it behaves as a function of time. In this system, we didn't give any description of space, right? Never said anything. We said, I measure 3 values. Where does it happen? Don't know. Didn't describe. Not relevant. Okay, so I want to know what's this gamma. For that, I need an additional information of how the system develops with time. What do I need in order to describe how the system develops with time? Schrödinger equation or the Hamiltonian? Somehow I have to know the Hamiltonian. Let's assume that for this system, someone comes and gives me the Hamiltonian. So I can someone comes in and says, I have thought long and hard, and this is a Hamiltonian. So what is the first thing you tell him? No.
The eigenvalues. Some
No.
of them aren't.
Tell him
Is this one?
you.
Multiply.
Are you crazy? Didn't you listen to what we have learned in class? This is not Hermitian. So you made a mistake in all your long and deep thinking about the system. Okay, it can't be because it's not Hermitian. Go home, come back with another answer. Okay, let's correct it. Now it's an Hermitian Hamiltonian. Could be that he's right.
But how can you look at it and straight away say that it's Hermitian?
How do you do it? Okay, let's look on this guy. Okay, what do I do when it's Hermitian? I do self-adjoint and complex. Okay, self-adjoint. Take this line and write it down here. Take this guy and write it down here. Take this guy and write it down here with the complex quantity. Okay? Is this equal to this? No. Go
So
home.
just check it that way because
So the easiest thing to check hermeticity is look on the Hamiltonian. The diagonal has always to be real. There's no way that the hermetic Diagonal doesn't change the position, and diagonalize. Okay, has to be equal 0. That's the canonical way in which we find eigenvalues of a matrix. Okay, let's write it down. 1 minus lambda. So this is this guy times lambda square. I times minus I is 1. So it's minus 1.
Oh, yeah.
Equals 0. This
Yes, we have minus
1, sorry, 1, 2, and lambda 3 is minus 1. Okay? Plus 3 values. So, first thing you learn from this exercise is you will measure only 2 values of energy. either 1 or minus 1. And you see that you can have degeneracies, lambdas that are equal. Now, if you're pedantic, and if you're writing down an exam, it's better to be pedantic, otherwise you have an endless question. Okay, this was some measurement, we didn't give it units. Here it's Hamiltonian, it has a units of
I wanted to say one the wave function.
Okay, two giveaways. What is a Hamiltonian from analytic mechanics or wherever you ran into Hamiltonians the first time? Kinetic energy plus potential energy, right? What appears in both terms? Energy. So it has to be units of energy. So let's put a constant here, E0, with units of energy. Nothing in the calculation changes, except that now we have two possible energies. Okay.
The process of finding the lambdas is known because I don't know. Like when you use the determinant rate of the
right, it's basic linear algebra, which tells you that if you have here basically you want to multiply it by x. Y, Z, right? This guy, Y, Z, right? And get, right? So I get a set of linear equations in order for it to be 0, Y0 because I subtracted. Oh, good. Okay. So I'm left with this term. Okay. Now I have to find the eigenvectors. Now I can go and write down this equation, put lambda and solve these equations. I can also be a bit more clever and look for a moment on this Hamiltonian, on this matrix. One of the first things that you have to try to understand, to see when you are getting a matrix, can you simplify it? Right? Again, we don't want to work harder than is necessary. And this matrix actually is a block matrix. It has two blocks because all this line is 0, all this line is 0. Right? So I don't have to go and solve a 3 by 3 matrix. Actually, there was no point in going and doing this full, because I immediately could tell you that there is an eigenvalue of 1 here. Because if I take the first energy eigenvector, it has to be 1, 0, 0. Look, I'll multiply it here. This is not in the game. And I'll get 1 or E0 as the eigenvalue. So actually, instead of going and doing this complicated, not so complicated, more complicated calculation, I could have immediately come and asked, well, what happens for this part of the matrix? Okay, because I know that any of the two upcoming eigenvectors will have a 0 in the first position. Because otherwise it will be scrambled and not an eigenvector. Okay, so I'm looking only on and I'll leave the E0 outside because it's multiplied on both sides and I can't forget about it. So I have 1 with value 1 and 1 with a value -1. That's the first equation. Okay, can solve it whatever way you like to solve it. Let's take y. It's this is y is minus okay, so it's for any value as long as
You get the freedom.
I have freedom and I have normalization.
Oh.
Okay, I have to remember all the time that x squared plus y squared is equal 1. Right?
Yeah.
It has to be normalized. So, with no loss of generality, let's choose.
Wait, even the sub block? I mean,
Because the first term is 0, right? I'm now looking on eigenvectors of the form. What's this? Right?
Oh.
So the first term will not contribute.
Okay.
Okay, so
But when it does, you need to add
if
something.
it does, it does. But we're solving a specific problem, right?
Okay.
This is not a lecture. This is a recitation. I'm solving a problem.
No, I mean like if when you go back to the Hamiltonian, then you have x, y, and z, and then wouldn't that be a problem?
No, because in a moment I write down all of the.
Okay.
Okay, so what do I have here? So I can take it as 0. this solves everything that appears here. Normalization, that's 1 over square root of 2. If I choose x arbitrarily as 1, the other guy will be minus I. Just now, very important, a lot of times it's an occurring problem with students, I don't know really why. They get a result, they don't check something was wrong. So you write an eigenvector, check if it's an eigenvector.
If you say that x is 1, and so y is minus I, how is the last equation satisfied?
This is satisfied?
No, this one.
Because of 1 over square root of 2.
Oh. Yeah, okay.
You want to be more methodical, be my guest. But it's
No,
easy to. Okay, let's go back and check it. Okay, 1, 0, 0, 0, 0, 0, I minus I 0 times 0, 1 minus I, it's 1 over square root of 2 because this doesn't make any difference. Check. 1, 0, lovely. Second 0, 0, I minus I. It will give you here 1, right? Minus I times 1 minus I. Great, I know to solve an order 2 linear equation. Set of equations with 2 variables. Look. So I can write down here and this is also easy. Okay? Okay, the last one. Minus. Okay, so it's minus here, plus here, and the third one will be minus y. Should check again, but okay. Am I all good? No. There is another check I have to do. This is a basis because the eigenvalues of eigenvectors of an operator are a basis. They must be orthogonal. Very important to check. That's a way to root out all kinds of silly mistakes. It's not complicated algebra, but still mistakes may occur. Okay, this times any one of these is immediately orthogonal.
Yeah.
This, okay, I have to take a complex conjugate because, let's say I'm doing E2, E3. So E2 would be 0 plus I, because it's a complex conjugate. So 1 plus I times 0, 1I, and this is 0. Fine, the only problem I have here, I forgot to copy the normalization. Okay, so we know all that is to be known about this Hamiltonian, this operator. We have the eigenvalues, we have the eigen. Now, the final part of the question. At time t0, I have psi given here. Okay? Then at time t, okay, at time t equals 0, I know that the probability of measuring of measuring 0 is half, right? Let's assume that at time t0 it was someone came and also still not well defined, right? We have this. Someone comes and tells us gamma equals 0. Okay? So what do I do here? Someone has an idea?
You need to get the wave function to the probability, so maybe by Fourier you can get the wave function over time. And then we say it equals the probability equals.
You're in the right direction. It will be something reminding Fourier, but not because we do a Fourier transform. quantum mechanics, as long as we don't perform a measurement, how does the wave function evolve?
You told me the once it was e to the Hamiltonian or something? I times.
If a simpler answer. It evolves according to the Hamiltonian. Right? We know the Hamiltonian, we know everything that we need to know about the Hamiltonian. So therefore, we're able to answer this question. Okay, so what do? We scratch our head a bit and remember that we actually gave a general solution for this situation in class, I think 2 meetings ago. What did we say? Psi of t.
Oh, the stationary circle.
It's stationary. Do you see time dependence in the Hamiltonian? No. Stationary. So what did we say one has to do? On all the values eigenvectors of the Hamiltonian, where these are the eigenvectors that we already calculated. Right? So basically, once we calculate this guy, we can go forward and know psi t at any time. Okay, so I'll go and perform the 3 elements, the 3 amplitudes that I have to calculate. I have psi 0, psi at time t0, I have E1, E2, E3. I have all the ingredients I need. Okay, I'll write this one down more conveniently. 0. Okay, let's roll. plus I because it's a complex conjugate. These things are important. It can change the outcome. 0. In this case, it's not important because I have 0 component here, but in general, yes. 1 over half E3 psi. Okay. Now, again, I'm checking myself. Each step, always when you're solving something, especially in an exam, check yourself.
It is a distribution. V squared.
Square of all these amplitudes has to be 1. Because I'm just in linear algebra speak, I transform to a different basis, right? That's all I did here. I went over from the basis of the original operator to the basis of the Hamiltonian. That's all I did here. Half plus quarter squared is equal 1. Okay. So now I have all the ingredients to write down my wave function explicitly. Have here the first one was 1 over square root of 2. And here I have E1, 1, 0, 0, and e to the power I E0. I'm writing down the explicit form. Plus 1 over 2 and I can rewrite it just for the amusement of term. we compare contributions from the first guy. Here I have contributions from both of them. Cosine or sine? Sine. It's cosine.
That's what.
Cosine. E to the power I something plus e is twice cosine. We have half here.
No, you need to have half there because you have half plus half, right?
I have
So
half.
you-
No.
Oh, correct. So it's okay. It's like that.
Ah, right. You have the I. Okay, go right. Stop the moment and stop at normal. This square, this is half, and this plus this is 1. Where would I do the mistake? So it's 2, where was it? So that's why you check normalization at each point, and actually the answer is 1 over square root of 2 appears now before everything. This is a nice normalized wave function, and I even discovered my mistake by checking it. Okay, what was our question? What is the probability of measuring 0? Measuring 0 corresponds to this amplitude, because I'm all the time working in the basis of A. P of measuring 0 is half cosine squared E0 T over H bar. Again, let's check at time 0. Great, cosine of 0 is half. What happened here from point of view of physics? Well, the operator A and the operator for the Hamiltonian have a different basis. Therefore, if I had some probability of measuring some value of A at a given time, it may change with time. Because the development is according to a different basis. And therefore, the fact that I had a probability half of measuring at time t equals 0 doesn't guarantee me that any time I measure t equals 0. Okay, that's the answer. Final part. How do I measure gamma? Okay. What happened here? Basically, nothing much. The only thing is that instead of this eigenfunction, where is it? Here. Right? That's all the change. So, anytime I have this guy, I have to add the gamma and sorry. So what will I have here? Will that change anything?
No.
In this case, it won't change anything. Homework. Come up with an initial wave function for which this gamma can change. I know it's not the traditional ways that you get homework, but it's a bit of thinking. How can we change the initial wave function so that gamma will play a role here? You have the freedom to choose any initial wave function that you want and check when the phase may give you a difference. Okay, so we'll stop here.
Thank you.
Thank you.
אני יכולה אותך לשאלה או שאתה תזוז?
קצר.
לא רציתי להכיר, אבל קודם הבנתי, הוא דיבר על נגדית, שמענו מה אפשר להגיד על הפצגה, שחדשים, ואז אמרנו, סיכוי לגדול, ולפי המקדמים של ה...
לא, של הפונקציית גל, של A, B ו-C.
כן.
כי אלו הם אייגן וקטור של A. זאת אומרת, הם נותנים את הפריסה של פונקציית הגל בבסיס הזה.
אוקיי.
הסיכוי למדוד איזשהו ערך של אופרטור הוא